next section is about looking at a symmetric curve, so one that is bell-shaped, and using the empirical rule to make some decisions about how much data is represented by that normal distribution. So if your data are skewed, if you have a tail, then you don't want to use this lesson for that kind of data. For that kind of data, you should make box and whisker plots, you should analyze the median, and you should look at the interquartile range to think about the spread of the data. So skewed data is not applicable to this situation. The situation is when you have symmetric data. When you have symmetric data, the empirical rule says that 68% of your data will be within one standard deviation of the mean. So you figure out the mean, you figure out the standard deviation, which we did on the calculator, and all of your data is going to be within the mean plus the standard deviation and the mean minus the standard deviation. 68% of your data. 95% of your data is going to be within 2 standard deviations of the mean. And really, almost all of your data will be within 3 standard deviations of the mean. 99.7% of your data values will be within 3 standard deviations of the mean. So what that means for us is that if we can figure out what the mean is, and we can figure out what the standard deviation is, then we can figure out kind of some distribution, some information about the distribution of the data. So in this example, in Minneapolis, Pizza Luce's delivery times follow a normal distribution with a mean of 30 minutes and a standard deviation of 5 minutes. Okay, so we know that 68% of the data is going to be within 30 plus 5, or 35, and 30 minus 5. It's the mean plus a standard deviation and the mean minus a standard deviation. So we know that the middle 68% of the data is going to be between 25 minutes and 35 minutes. So more than half of the deliveries are going to be between those 2 time periods. If I wanted to know the 2.5 fastest delivery, so I want 2.5% of the fastest deliveries, I know that 95% of all of the data values will be within 20 and 40 minutes because that's 2 standard deviations. That means that 5% of people either wait less than 20 minutes or more than 40 minutes. So 2.5 are going to be on each end because it's symmetric. It's 100 minus 95 would give you 5%. So 5% of people are waiting for longer than 40 or less than 20. But then because it's symmetric, we divide that by 2. So we know that 2.5% are waiting more than 40 and 2.5% are waiting less than 20. So wait times of less than 20 minutes represent the fastest 2.5%. The middle 95% of the data falls within 2 standard deviations, so the middle 95% of the data falls between 20 minutes and 40 minutes. The things that change for your normal distribution are going to be what your mean are and what your standard deviation are. The things that don't change are the 68%, the 95%, and the 99.7%. That's always the same. The only thing you're doing is changing what values you're using for your mean and for your standard deviation. Okay, so here's a second example. We have a mean birth weight for babies is 7.6 pounds. The standard deviation is 1.3 pounds, and the distribution is normal. So that tells us we have symmetric data. So we're going to fill in our values on this bell graph. The mean is 7.6, and then we're going to count by 1.3. So if I add 1.3, that's the standard deviation. This would be 8.9 If I add another 1.3, that would be 10.2. And then I'm going to go backwards by 1.3, so that would be 6.3. And then I go backwards one more time, and that would be 5. Okay. So between what two weights do 95% of babies weigh? So we have 1 standard deviation, 2 standard deviations. So between 5 and 10.2, 95% of all babies are between 5 pounds and 10.2 pounds. What weight would the heaviest 16% of babies be above? So we know that 68% is within 1 standard deviation. So if I do 100 minus 68, I'm just doing a little scratch work here. 100 minus 68 would be 32. So that means that 16% are going to be above this value, and 16% are going to be below that value, because 32 divided by 2 is 16. So the heaviest 16% of babies are going to be above 8.9 pounds. And then if we wanted to write 2 more statements about the birth weight of babies, we could say something like half of all babies are above 7.6 pounds. So here's 7.6, that's our median. That would be one thing we could say. And we could also say, this is 6.3, we could say that this is, I don't know, there are lots of different things you could say, but one thing you could say is that the middle 68% are between 6.3 and 8.9. Z-score is a way of measuring how many standard deviations a data point is from the mean. So the Z-score tells you how far off your data are from the actual mean value. To find the Z-score, you subtract your data value minus the mean, and then you divide by what the standard deviation is. So the mean and the standard deviation depends on your data set, and then your data value depends on which value you're comparing to the data set. So here's an example. The SAT and ACT are 2 tests that seniors take to get into college, and it's hard to compare an SAT score and an ACT score because they have different scales. But if I want to figure out which one is a better test, I could look at what their Z-scores are. So if I'm looking at Ella's score, she took the SAT, so I'm going to use her mean and her standard deviation. And her Z-score is going to be her value, 1380, minus the mean, divided by the standard deviation. So that means that if I grab my calculator, Ella has a Z-score of 1.9. And since her Z-score is 1.9, that means that she's above average, and she's actually almost 2 standard deviations above the mean, so she's doing very well. Now if I look at Alicia's Z-score is going to be based on the ACT, so hers is going to be, her score was 32, and we're going to use the ACT data for her score. So 32 minus 21 would be 6 over, no it wouldn't, it'd be 11 over 5, wouldn't it? Yeah, it would. So her Z-score would be 11 divided by 5. 2.2, and 2.2 is going to be a better Z-score than Ella's. So Alicia's score is actually better because she has a Z-score of 2.2. She's more than 2 standard deviations above the mean. For tonight's homework, I'm asking you to find something that has a normal distribution. It might be good to think of an idea of something and just do a Google search that says, what is the mean and standard deviation for? So like I looked up mean standard deviation baby weights when I was making this presentation. So Google things that you think probably follow a normal distribution, shoe size maybe for women or something like that, and then Google that and find the mean and standard deviation. Okay, good luck, have fun.